everyone. Thank you for joining today's webinar. My name is Sakshi Sethi. I manage the OIDA membership program here at OSA. I'm really excited to introduce today's presentation by one of our corporate members, VPIphotonics. I'm going to go ahead and turn things over to our moderator, Chris Maloney. He's the Director of Business Development at VPI. He'll introduce our speakers and get us started. Thanks.
Thank you, Sakshi, and thank you everybody for joining us today. You'll be hearing from Dr. Ilyas Giacomitis, a project manager at VPIphotonics, and Dr. Abdelkarim Amari, who's a senior application engineer. And they both, their research has been focused in coherent optical systems, so they're experts in this. So to get started with the agenda for today's webinar, again, the title is Advanced DSP Encoding for Next Generation Coherent Optical Systems. And I'll be discussing some background and some trends in optical systems. Ilyas will talk about digital signal processing for fiber nonlinearity mitigation and some techniques involved there, and actually give a live demo in VPI Design Suite. And then at the end, Karim will discuss advanced modulation formats and coding, in particular, the hot topic of probabilistic shaping, and he will also give a live demo there. And again, please feel free to ask questions throughout, and we'll follow up at the end with a Q&A session. So I'll kick things off. So first, I want to address why we're even discussing this topic today. So as most of you are probably aware, global internet traffic is growing rapidly due to things like the Internet of Things with machine-to-machine connections, increased video definition, the number of connected devices, the list goes on. So to keep up with this increase in demand, faster Ethernet speeds are required. And so as you can see, the standards still need to be developed for some of the faster speeds. And to do that, it's not as simple as just increasing the switching speeds, as there are some performance limitations in the electronics. So to transmit more data, instead of switching faster, one thing that we can do is use fatter pipes. So one method here would be parallelization. And so that would include things like fiber, wavelength, or space division multiplexing. And another option, which we can use together, is higher modulation formats, higher order modulation formats. So non-return to zero, PAM4, starts to increase the number of bits transmitted per sample. And today we'll actually be discussing coherent modulation, which further addresses that. So for those of you who are unfamiliar, I just want to give a brief introduction to some of the various modulation formats. The first, the most simple, is this non-return to zero, NRZ, direct detection. So this is amplitude modulation with only 2 levels to transmit one bit per symbol. Moving up in complexity, we have pulse amplitude modulation. So 4 or more amplitude levels can be used to transmit signals. And in the case of PAM4, 1 gigabaud would equal 2 gigabits per symbol transmitted. And then finally, for coherent detection, one popular method is this quadrature amplitude modulation, or QAM, where both amplitude and phase can be modulated. And oftentimes polarization is used as a third dimension to transmit and represent a higher number of bits per symbol. So currently, coherent detection is the mainstream choice for long-haul networks, mainly for the reason that it's more tolerant towards optical impairments, such as chromatic dispersion. And direct detect techniques are used at shorter link distances. So, for example, inside of the data center. And techniques like PAM4 and NRZ are a lower cost option for these shorter links because they don't require the complex DSP ASIC, but they do have their own data rate limitations. So for faster bit rates, new solutions continue to be revealed and more advanced modulation formats are being utilized, like dual polarization, 16 QAM, And we're also seeing PAM4 start to displace NRZ modulation for shorter links. And new solutions and demonstrations are also emerging for even faster bit rates. So for example, 800G 1.6 terabyte systems, they're starting to use higher order modulation formats and techniques like this probabilistic shaped constellations. And we're also starting to hear people ask when coherent detection will enter the data center, which I don't have an answer for you. But what I can say is now is an exciting time to be exploring and evaluating these new solutions. So at VPIphotonics, we have over 20 years of experience serving the photonics industry with international operations out of Berlin, Boston, and Minsk. And we believe in empowering you to define the cutting edge. So the way we do that is by making our products interoperable, integrated, and industry leading. And we provide professional simulation software at various levels of abstraction. So at the device level, we allow for the analysis and optimization of waveguides and optical fibers. At the component level, this includes the design of photonic integrated circuits and fiber lasers and amplifiers. We can move up to the system level for designing and optimizing transmission systems. And we go all the way up to the link level for things like cost optimized equipment configuration. And we also provide some technology consulting. And in particular, we're heavily involved in many European forward-looking research projects as well. So this shows a glimpse into our product portfolio, what we offer, and you can see these different abstraction levels represented here. And I'm not going to go through all of these, but today we're going to be focusing on this VPI transmission maker optical systems tool. And within that, we have our own DSP algorithms, but I want to point out we also have an additional VPI toolkit for a DSP library, which was developed at Fraunhofer HHI for some additional DSP algorithms as well. And now this tool works inside of our VPI Design Suite. This is our design environment, which includes both transmission and component design in the same user interface. So here we actually see a screenshot of the VPI Design Suite. So on the left side, you'll see all of these electrical and optical modules. We have a large number of application examples. But what I want to point out is how our photonic circuits tool is integrated within optical systems. So on the right side, you can actually see the design of a photonic integrated circuit. And in particular, this is a Mach-Zehnder modulator. And what we can do here is actually represent this as a building block. So you can actually see the building block here in our system design. So we have our transmitter optics, our optical fiber, and our receiver optics here. So this is all integrated into one design environment. And then we also are highly interoperable with many different third-party softwares. So one that I'll point out is we have a strong relationship with Keysight, and we've recently developed some electrical optical co-design and simulation tools there. And then today in the live demos, you'll see all of our data visualization and analysis tools as well. So that's all I have. I'm going to now turn things over to Ilias, who's going to discuss digital signal processing for fiber nonlinearity mitigation.
So thank you, Chris. In this part, I will discuss two important digital solutions for compensation of both linear and nonlinear effects in coherent optical systems that can support transmission capacities of 100 gigabits per second and above. So the model coherent transmission systems in VPI are highly flexible, permitting modulation of different channels and digital subcarriers per optical wavelength. They also enable escalation of the symbol rate and bits per symbol using high order modulation formats, such as QAM, quadrant rapid modulation, phase shift keying, and differential coding. Circular CM QAM modulation formats are also supported for flexible constellation designs, but they use automatic or parameter-defined constellation. We also have we also support QAM constellations that can be arbitrary and can be defined from a text file. Now, for realistic transmission over non-dispersion managed bands using, for example, 16 or 64 QAM, we first implement in the transmitter side a traditional polarization multiplex QAM signal that uses a pair of Mach-Zehnder modulators. Using also this driver block here, we can perform also pre-distortion in order to perform Mach-Zehnder modulation linearization. Then after boosting the signal through an optical amplifier, we boost it with the desired power through a recirculating loop, including inline amplification, so we can compensate for the fiber losses. At the receiver side, we have a block here that is used to restore the state of polarization. This is for the case the signal is affected from polarization mode dispersion and radon birefringence. For converting now the optical signal to electrical, we use inside this signal, this Galaxy module, traditional polarization diversity coherent receiver that includes 2 coherent receivers for detecting the 2 orthogonal polarizations of the signal, and also includes realistic analog to digital conversion. Now, using the VPI DSP library, we can now perform the 7 required DSP steps for equalizing a QAM signal in a realistic scenario. So after the analog to digital conversion, the signal first passes through IQ imbalance correction for potential phase and amplitude imbalance in the 90-degree optical hybrid. The next highlighted block here is the one that performs chromatic dispersion compensation using a frequency domain equalizer with the FFT and IFFT convolution algorithms. But we also can use, by choice, the digital backpropagation. We can compensate both chromatic dispersion and fiber-induced nonlinear distortions. And the DBP algorithm, the digital backpropagation algorithm, I will detail in the next slide. Now, then close phase recovery is required when the sampling rate at the receiver clock is asynchronous to the transmitter clock. The 4th block here is an adaptive time domain equalizer of 2x2 minus structure that uses the constant modulus algorithm for BPSK, QPSK, and the multimodulus algorithm for high order QAM formats, and is used to demultiplex for crosstalk between X and Y polarization and recover any residual misalignment between transmitter and receiver state of polarization, and also any residual polarization mode dispersion. Afterwards, the signal is downsampled to the baud rate. So we actually throw away samples by selecting the sampling time with a maximum mean power. In the final 2 blocks before the modulation, carrier frequency recovery is performed to correct the frequency mismatch between the transmitter and receiver laser, and then carrier phase recovery is performed using different algorithms. The selected one here is the blind phase search, but we have also option to use the Viterbi block or sliding window or maximum likelihood. So now if we want to increase the order of modulation, for example, for 16 QAM to 64 QAM, for the same transmission distance, then we should change besides the number of the bits per symbol constellation and format, but also the number of pre-symbols parameters in the blind phase search algorithm that estimates the phase error, and the adaptation speed, or else called step size in the adaptive filter, which changes the tracking capabilities of the algorithm. The digital backpropagation algorithm, on the other hand, essentially rewinds the nonlinear channel to compensate carrier-induced nonlinearities, such as self-phase modulation that arise at high signal powers. In digital backpropagation, the optical channel is numerical modeled using the inverse of the nonlinear Schrodinger equation that is expressed with Markov equations for dual polarization systems. The received signals are digital backpropagated through this modeled virtual channel with the help of the split-step Fourier method. There is also another method that can improve the nonlinearity tolerance, and this is the digital subcarrier multiplexing. And in this method, we split the high baud rate single carrier signal into many multiplex low baud rate subcarriers. And this is done using closely spaced Nyquist subcarriers that are created in the electrical domain and modulated in a single optical wavelength. Such as transmitter is actually highly flexible in VPI and easy to use, and in which we can load any number of subcarriers that can have also different modulation format levels. As we can see here, for example, the first subcarrier can have QPSK, the second one can have 16 QAM, etc. This scheme is proven to be tolerant to nonlinear interference noise compared to the conventional single carrier QAM. And this can be explained by the theory of four-wave mixing efficiency or the walk-off between subcarriers due to chromatic dispersion. So the first demonstration, I will show from the previous mentioned 16 QAM and 64 QAM system at 200 and 300 gigabits per second respectively, for 200 kilometers fiber transmission using a 100 kilometer span length. And I will show also the impact of digital backpropagation on the system performance. At the receiver DSP, as we can see here, we have selected the blind phase search algorithm and also the important parameter of the number per symbols, for which are 5 are enough for the 16 QAM modulation. So first I will run this sweep, which is essentially the bit error rate versus the transmitted power for average X and Y polarization. And we can clearly see that at low powers, the system is degraded due to the as a noise from optical amplification. But while we have higher powers, then we are dominated by nonlinearity. So for this case, is the self-phase modulation. Now I will repeat this process, but I will change in the DSP library in this block. Instead of chromatic dispersion compensation only, I will change to digital backpropagation. And I will set it to 40 steps per span. And I will run the sweep again. So now, if I compare this curve now with the previous one, we can see that at optimum and higher powers, we have improved bit error rate. This is because we compensate self-phase modulation with digital backpropagation. Now, if we want to move to higher order modulation format, I'm going to run directly this visual design assistant macro-based. So with this button, we can automatically change the parameters we want to do. So we can change the number, the bits per symbol from 4 to 6 for 64 QAM. And then the number of per symbols are changed, and also the adaptation speed and the constellation format. And so for simplicity here now, I will run it once at the fixed optical power at 4 dBn. So you can clearly see now the 64 QAM signal with a bit error rate of 0.02. And now I will run again the system from chromatic dispersion compensation. I'm going to move to digital backpropagation again at 40 steps per span and do a single run and compare. So we can see now that the bit error rate has been decreased to 0.01. Now in the next demonstration, I will show the use of dual polarization digital subcarrier multiplexing for transmission of 256 gigabits per second over 750 kilometers of single mode fiber. At the receiver, as we can see here, a similar DSP unit is employed for demodulation, where chromatic dispersion is first performed, but then an RF demodulation of a selector subcarrier is performed by the single sideband demodulation algorithm here. And after using this block, then the whole processing is the same with standard algorithms for single carrier QAM. So first I will run the schematic for 4 digital subcarriers for a fixed 16 QAM modulation format. So that will be 8 gigabaud per subcarrier. So we will have total 38 gigabaud. So you can see here the 4 digital subcarriers generated. then transmitted, and then received. And you can see here actually that we have selected the first lowest frequency subcarrier for demodulation. And then we calculate the symbol error rate for this one only. And now I will change from 4 subcarriers only to 1. So essentially we don't have digital subcarrier multiplexing, but that will be for 32 gigabaud. So for the same data rate. And I will do a single run. So you can see here in the spectrum, the electrical spectrum, we have a total 32 gigabaud signal and the corresponding symbol error rate. But now you can see that it is more decurated. So that means that even though the data rate is the same as before, the symbol error rate actually is worse. So this is because nonlinear distortions are more severe in this case. So also note in this demo that you can change any modulation format level you want for each subcarrier. For example, you can use QPSK with 2, 16 QAM with 4. And you can do the same process with bit loading to maximize transmission performance. So thank you all for your attention.
Yes, thank you, Ilias. Thank you for those great demonstrations for digital backpropagation and digital subcarrier multiplexing. Yeah, it was really useful. So we're actually going to turn things over now to Karim, who's going to discuss advanced modulation formats and coding. And it looks like we can see your screen, Karim. So please, the floor is yours.
Okay, thank you very much, Chris. So previously, Ilias showed some DSP to compensate for the impairments due to the optical link and the components. And in this part, we will focus more on how to adapt the signal to the channel. And this can be done by using advanced modulation formats, such as probabilistic shaping and multi-dimensional modulation, and also forward error correction FEC for optical systems. Then I will show some live demo regarding these techniques. Let's start first by the probabilistic shaping. The main idea of probabilistic shaping is to approach the channel capacity by targeting a non-uniform distribution on the input symbols. And this will lead to the increase of the minimum Euclidean distance and then increase the performance. The optimal distribution for the IWGN channel is the Gaussian distribution in continuous time and the Maxwell-Boltzmann distribution in discrete time. And by using this distribution, we can achieve up to 1.53 dB gain as an ultimate shaping gain. And this gain increases with the block length. So the higher the block length, the shaping block length, the higher is the performance. In optical communication systems, it has been shown that short block length provide better performance than long block length case because it provides both shaping gain and also nonlinear tolerance, especially when sphere shaping is used because it has also low rate loss at short block length. Let's look at this constellation here. So this is a 64 QAM, a uniform 64 QAM. As you can see that this axis is I and Q, and then here we have the PDF, the probability distribution. All samples have the same probability of occurrence, and the spectral efficiency is 6 bits per sample with a minimum Euclidean distance of 0.22 at the unit average power. If we apply probabilistic shaping to target the Gaussian distribution, we will see that here the inner points will have more probability of occurrence than the outer corner points. And this leads to an increase in minimum Euclidean distance to 0.3 at the same average power, but with a loss in spectral efficiency due to the shaping. If we do more shapings, we get higher minimum Euclidean distance and higher performance, 0.43 here, but with lower spectral efficiency. In practical, to have a fair comparison between uniform distribution and probabilistic shaping, we have to compare at the same net bitrate. So we have to compensate for this spectral efficiency loss due to shaping. This can be done by using higher sample rate for shaping or different FEC overhead, higher overhead for uniform distribution. And the third option is that we do more shaping until getting like 4 bits per symbol as spectral efficiency for shape at 64 QAM, which is the same as 16 QAM. And then we compare shape at 64 QAM versus 16 QAM at the same spectral efficiency. And I will show later that by doing this, we can get better performance using shape at 64 QAM in comparison with 16 QAM. In VPI Design Suite, we have some models for probabilistic shaping. So at the transmitter side, we have the PS encoder and the decoder at the receiver side for the deshaping. And we can do multiple options for probabilistic shaping. We can apply shaping for QAM modulation. Also, we can combine it with FEC via the pass framework, in which the parity bits of FEC are used as sign bits for the shaped amplitude. And we can do shaping for arbitrary modulation as well. Let's move now to the second part, which is the multidimensional modulation. Firstly, for the conventional modulation formats like QPSK, as it's shown here, we have I and Q, imaginary and real axis for polarization X, and similarly for polarization Y. So the optimization of the constellation points is done in 2D space, in I and Q for polarization X, and same for polarization Y, but we have completely independent signals in polarization X and Y. In multi-dimensional modulation, this optimization is performed in n dimension. That can be 4 or higher. For example, in this case, if we transmit green sample in polarization X, we transmit red sample in polarization Y. And then the signal in polarization Y is constrained based on the signal of polarization X. And then we have 2-dependent polarization, and this is 4-dimensional modulation. And of course, this dependency is not random, is chosen so that it increases the minimum Euclidean distance. And there's some known approach for this, like set partitioning modulation, and also to mitigate some effects such as cross-polarization modulation by having a 0 degree of polarization. Multi-dimensional modulation can be done in polarization-based 4D, as it's shown here, but also it can be done in time slots, so that time slot 2 has dependent signal on time slot 1, and so on. And it can be also done in space division multiplexing as a spatial dimension by having dependent signal or symbol on multiple modes in multi-mode fiber or multiple cores in multi-core fibers. Multi-dimensional modulation and also probabilistic shaping provide 2 main advantages. The first one is the performance improvement, and the second also important advantage is they provide finer granularity for flexible optical transponders, which are a key technology of next generation elastic optical networks, in which the bitrate is adapted according to the network demands. So by using probabilistic shaping and multidimensional modulation, we can change the spectral efficiency of the transponders, make it more flexible, and this is required for elastic optical networks. In VPI Design Suite, you have multiple models for mapping. So we have the 2D mapping, the classic for classic QAM and PSK and other modulation. It supports also arbitrary modulation. Then we have the 4D mapper for 4D symbols, 4D modulation. And then multi-dimensional mapper for higher than 4D, like 8D and 12D and so on. At the receiver side, we have the bit error rate 4D that works for 2D, that works for 2D modulation, 4D, and also pole mix in which X and Y are independent. Then we have the multi-dimensional bit error rate for multi-dimensional modulation. And the first output here is the performance metrics. It can be bit error rate, symbol error rate based on Monte Carlo or also Gaussian fitting, EVM, and also material information and generalized material information, which are more accurate for probabilistic shaping and soft decision decoding. Then the second output is the signal. It can be the detected bit sequence or detected symbols, and also log likelihood ratio, LLRs, that can be used for soft decision decoding. Let's move now to the FEC for optical communication. So the main idea of FEC is to reduce the required SNR at a given bit error rate. And this is known as the coding gain, which is the reduction in terms of required SNR at a given bit error rate. We have also the net coding gain, which is coding gain with correction by considering the penalty due to the bitrate increase. The typical value of bit error rate in which we calculate the net coding gain is 10 minus 15. In optical communication systems, we have mainly three generations of FEC coding. The first generation, standardized of FEC coding. The first one used Reed-Solomon codes with an overhead of 7%, which means that 7% of the data is parity bits from the coding, and with a net coding gain of 6 dB. The second generation also use overhead of 7% and target net coding gain of 8 to 9 dB. And it uses concatenated code, interleaving for avoiding burst errors, and also iterative hard decision decoding. It was standardized in 10G and 40G WDM system. And the types of codes using are the BCH codes, Reed-Solomon, and LDPC codes. The third generation allows higher overhead to 15% to 25% with higher coding gain of more than 10 dB net coding gain. And it uses soft decision with iterative decoding. Soft decision decoding provide better performance in comparison with hard decision, up to 2 to 3 dB gain, but with high complexity. So we have the trade-off between complexity and performance. And recent research works focus on the region between hard decision and soft decision, so that having complexity close to hard decision with a gain close to soft decision by using some soft information. The type of codes used in this third generation are the LDPC codes and turbo product codes. In VPI Design Suite, we have implemented multiple FEC coding, including Reed-Solomon, BCH code, Hamming codes, LDPC, and irregular repeat LDPC, which are used in standard DVPS2, and they have better performance and low complexity than the regular LDPC. Let's move now to the VPI Design Suite to show some demonstration. Firstly, here we have we compare probabilistic shaping with the QAM modulation, shaped 64 QAM versus 16 QAM at the same spectral efficiency of 4 bits per symbol. So here we have the PSO encoder, and we have, as I mentioned, multiple options for probabilistic shaping, including FEC and also arbitrary. Then we consider a back-to-back scenario, and at the receiver side, the bit error rate is used in 2D mode because we already separated X and Y here. If we run the OSA performance, and here we have the constellation for 16 QAM and the shaped 64 QAM. And here we have the probability distribution of the shaped signal. So as you can see that the inner points have more probability of occurrence than the outer points. And we have this shaped the 64 QAM here. And here we have the material information versus the OSNR. As you can see that shaped 64 has better performance at low OSNR than 16 QAM. And at high OSNR, both of them converge to the entropy, which is 4 bits per symbol. For the second demo is for n-dimensional coding for space division multiplexing. So we consider 12 dimension for space division multiplexing. And we use this multi-dimensional mapper. And the mapping is included as a file here. And you can see how it's done. So here we have the bit sequence and the corresponding symbols. It's 12 dimension symbols. So we have first I and Q for polarization X, I and Q for polarization Y. This is for the first mode. Then we have second mode and third mode. So we have this 12 dimension is correspond to one symbol. And we consider a few mode fibers with 3 modes. And here we have this coupling that combine several single mode optical signal to the multi-mode output. Use it for the multi-mode fiber here. And we want to see the impulse response and the constellation. Let's run the simulation here. At the receiver side, we use the bit error rate and dimension. And here we have a MIMO equalizer for the modes. So firstly, here we have the impulse response of the few mode fiber. And then we have the spectrum, electrical spectrum. Then we have the constellation. So we have 6 constellation here, but it corresponds to one symbol because we have 12 dimension symbols. So this one for polarization X for mode 1, polarization X, Y for mode 1, then the same for mode 2 and 3. The last demo to show is for concatenated FEC encoding and decoding under the DVPS2 standards. So in DVPS2, concatenated codes are used. So we have the we have BCH codes as outer codes and LDPC ERA, irregular repeat, as inner codes. So here we have the options for multiple codes, LDPC, Hamming, BCH, and we can include the parity check matrix here. And you can choose the code rate. We support also multiple code rates for LDPC ERA. We consider IWGN channel. And we use this interleaver to avoid burst errors. At the receiver side, we do first decoding for LDPC ARA, then VCH. And we have multiple options for decoding, so we can use sum product and mean sum for soft decision decoding. And we count the bit error rate here after FEC. Let's run the ASANAR performance. So here we have the constellations and the bit error rate after after FEC versus the ASANAR. Here we have the evolution of the constellation, and here, as you can see, that the higher is the ASANAR, the better is the performance, of course. And then we can see that we achieve lower bit error rate at higher ASANAR. And then we achieve 0 bit error rate because we don't use a large number of code words. And if you increase the number of code words, we can achieve lower bit error rate to 10⁻⁷ or so. So that's all from my side. I give the floor to Chris again.
Yes, thank you, Karim. Thank you for that demonstrations and deep discussion around probabilistic shaping and advanced coding. So actually, I just want to thank our speakers, Ilyas and Karim, for that. And thank you everybody for your attention. You can see our email addresses are being displayed on the screen right now, so feel free to reach out to us. You can also visit our website, and you can ask about a free VPI Design Suite software evaluation as well. And if you're interested in news from VPIphotonics, at the bottom of our website, you can subscribe to news there. So thank you again, everybody, for your attention. Thank you, Ilyas and Abdel Karim.
Thank you
very much.
guys. Thanks. And thank you all for attending. And I'll let this information sit on the screen for just another couple of seconds. So thank you, Chris, Ilyas, and Karim for the presentation. If anyone has any questions, again, please feel free to email them directly at this point. So have a great rest of the week, and thank you all again.
Bye.
Thank you.
Bye.